Welcome to the electronicshobbyblog.com. This is the first of 4 lessons on resistors. We'll start with Resistor Basics, then talk about resistors and circuits, including Ohm's law and Kirchhoff's voltage and current laws. Then we'll look at potentiometers, which are a form of variable resistor. And then finally, we'll look at resistor-based sensors. So let's get started. Resistors are the most used component in electronics. They appear in almost every circuit. Even when a circuit has no physical resistors, it still has resistance. Parasitic resistance, as well as parasitic impedance, another form of resistance, occur naturally in all components, including wires and circuit board traces. Resistors, as the name implies, resist the flow of current. We use them in circuits to limit or control the amount of current reaching other components, or to create a drop in voltage. A resistor is analogous to a valve in a pipe system. The valve can reduce the flow of liquid and create a drop in pressure on the other side. Resistors do that same thing for voltage and current. Unlike other electronic components, a resistor has no polarity. It can be inserted in the circuit in either direction. Resistors also come in both fixed value types and variable types. A variable type resistor is called a potentiometer. And potentiometers are very useful in that they can be installed in circuits and be used to adjust the resistance in things like volume controls or when doing calibrations. There are both American symbols and European symbols for resistors, and then different symbols for a fixed resistor versus a variable resistor or potentiometer. Resistors are available in many different values, power ratings, and tolerance. The tolerance indicates how closely the actual value of the resistor, which is normally measured with an ohm meter, matches the specified resistance. Tolerances can be very small, less than 0.1% of a difference from stated value, all the way up to 20%. It's important to use accurate resistors in precision applications. The smaller the tolerance number, the more accurate the resistance. For other applications, like lighting an LED, tolerance isn't all that important. Keep in mind, the lower the resistor's tolerance, the more difficult it is to manufacture, and the higher the cost. Resistors come in many shapes and sizes, from large power resistors, some which have holes drilled in them so they're intended to be mounted on a heatsink, to tiny chip resistors that are just a millimeter or so across that are designed to be mounted on printed circuit boards. All resistors dissipate power in the form of heat. The power the resistor dissipates during operation is a product of the voltage and current to which the resistor is subjected. Resistors are power weighted in watts. And, as form follows function, power rating normally follows intended application. The almost infinite applications in which resistors are used means they're available in a great number of power ratings, from less than 1/8 of a watt to more than hundreds of watts. Resistors are made from a number of different materials, depending on the required application, size, power rating, and tolerance. There are resistors that are carbon composition, which is essentially a carbon paste that's formed into the shape of a resistor. Carbon film resistors, where there's a thin film of carbon that's wrapped around a substrate. Metal film resistors, used quite often in chip resistors. Metal oxide film resistors, similar to carbon film resistors. Wire wound resistors. Power resistors are normally wire wound, where a nichrome wire is wrapped around a ceramic substrate. And then foil resistors, also used in chip resistor application. Resistor values are stated in ohms after George Ohm, a German physicist, teacher, and electrical pioneer who discovered the relationship between voltage, current, resistance, and power. That's Ohm's law, and we'll talk about that in the next lesson. The units, ohms, are abbreviated using the Greek capital letter omega. Resistors come in standard values. Some types and tolerances of resistors come in more off-the-shelf values than others. And while you may not always find the exact value that you calculate for a particular application, you'll almost always find one that's close enough to substitute. For example, you can see in this table of 5% tolerance quarter-watt resistors just how many different values are available. And if you calculate 123 ohms for your application, well, there isn't a 123 ohm resistor, but there is a 120 ohm resistor, which is pretty close, and it'll probably work just fine. Resistors are labeled with their value in different ways, depending on the tolerance, the size of the resistor, the manufacturer, and so on. The most common methods of labeling resistors are using color bands, either 3, 4, 5, or 6 color bands, depending on the tolerance, or a numeric code, or the actual value written right on the resistor. If you look at the graphic of colored bands, you can see that they have special meaning depending on the location of the band on the resistor, essentially the order of the band. And each colored stripe relates to a value, a multiplier, or a percent. It's important to be able to learn to read resistor values. And while you might not pick it up right away, there are a number of calculators on the internet that you can use to find out the value by simply plugging in the colors of the stripes or the numeric code. I'll put the links for those down in the description of the video. Common value abbreviations you'll see used with resistors are K, meaning kiloohm or 1,000 ohms, M, meaning mega ohms or 1 million ohms. For example, a resistor that's marked 1.5K is actually 1.5 times 1,000, or 1,500 ohms. Another common code system, used primarily with chip resistors, uses the letters R, K, or M as the decimal point. You'll often see this on schematics. The placement of the R, K, or M within the code tells you how to read the value. For instance, R33 means 0.33 ohms. 3R3 means 3.3 ohms. 3K3 would mean 3,300 ohms, or 3.3K. So you'll see that the symbol R, K, or M actually takes the place of the decimal point and tells you the multiplier at the same time. Like I said, don't worry if you don't get it at first. There's a bunch of resistor calculators on the internet. You can either search for one or look at one of the links that I've placed down below in the description. When choosing a resistor, it's important to understand the application. Do you need very accurate resistors, ones with a very low tolerance? How does the resistor need to behave with respect to temperature? Does it need to be extremely temperature stable? Some resistors, called thermistors, which we'll learn about in Lesson 4, are specifically designed to correlate their resistance to temperature. They're used in applications for thermostats and other temperature sensing applications. Other resistors are sensitive to light and vary their resistance in proportion to the amount of light striking the device. Don't ever forget about power handling. Power resistors are large so they can withstand heat. Resistors dissipate power in the form of heat, and it's important to understand the power that the resistor needs to dissipate in your application. A resistor that's power rated too low for your application can lead to disaster and even cause a fire. All electronic components, remember you heard this here first, contain magic smoke, and it's that magic smoke that makes the part work and do the things it does. If you apply more power than that part can handle, the magic smoke's going to come out, and the device just won't function the same afterward. And the house will smell too, trust me. I've released plenty of magic smoke over my lifetime. Well, that does it for this segment. If you enjoyed it, give me a like and a share. And if you want to learn more, come back for the next episode, Resistor Circuits. Thanks. See you soon.